Oh, class. Okay, so we're going to talk about torque today. So this goes back to mechanics. And so I drew a situation here where, say we have an object that can rotate about this pivot here. There's like an axis here, free to rotate about that axis. And say we apply a force a distance r from that axis of rotation. And, you know, the force could be at any angle. So I just drew kind of an arbitrary one. And we'll define r as a distance from the axis of rotation to where the force is applied. And so, you know, that's I drew like an r vector would point from the axis of rotation to where the force is applied. But, that points in a particular direction. And so the magnitude of the torque is that distance r times the force times the sine of the angle between these two vectors. So if we draw a line in the direction of r, if we just extend it, the force is at an angle there. The direction between them, I called phi instead of theta. And the reason why, we're going to look at the torque exerted by a magnetic field on a current carrying wire. And so let's go to that equation. We'll write down the equation here. I is the current, L is the length of the wire, B is the magnetic field, and we also have an angle in this equation. And so I gave them different names. This is a Greek letter phi, that's theta, because we don't want to mix those two up. So, yeah, if we have a wire that's in a magnetic field, there's a force on it. If that wire can rotate, there can be a torque on the wire. And that's what we want to talk about. Specifically, what we have is represented by these two pictures here. So like, this is from one perspective. Say we have a loop. Now I drew it as a square. We're going to look at the torque on a square wire just because that's easier. Now, if you wanted to make a loop of wire, what you do is you'd wrap it around a cylinder or something. It would typically be circular. But the result we get is going to be more, just apply whatever shape we have. And it's a lot easier to calculate with a square wire than with a circular one. So anyways, we have one wire carrying a current. So the current is I. So the current, these two wires are right next to each other. So it goes up, loops around in this square fashion, and goes down. Now this whole coil is in a magnetic field like this. So this is like a top view. You're looking down on this coil. So like here, you're looking at the top of the wire. What you're looking at from this perspective, you're seeing this wire here. So if you look at this end, you see the current coming up, and then it's going to go down the wire in this direction, and then it's going down. So from this perspective, if you're looking down on the wire, you see the current coming towards you, going down the wire, and then going away. So we can see what directions the currents are. And what we want to do is calculate the torque on this coil. So actually what I'm going to do is, just to be clear, we have an axis of rotation like this. So the wire's wrapped around something to maintain its shape, and it can spin around on this axis. And so what happens if we place this coil, we give it a current, and place it in a magnetic field. And so there's going to be forces on the wires, and because they're free to rotate, we can have a torque here. And that's what we want to calculate. So, let's get to that. So there's 4 wires here, like 4 segments. It's one wire, continuous wire, but there's 4 segments to it. And so let's look at, again, we're going to have to, it's a good thing, review the right-hand rule again. Let's look at this wire here. So it's in this direction. It's coming out of the board. And the magnetic field is in this direction. So in our right-hand rule, for a wire, we picture a wire as just positive charges moving in the direction of the current. So if you put your fingers in the direction of the current and curl towards the magnetic field, there's going to be an upward force. So there's an upward force from this perspective. And again, you could rotate the coil a little bit and it's still going to be directly upwards because the current is always up. It doesn't matter if you change the orientation. It's perpendicular to that magnetic field, so it's pointing straight up. Now let's look at this top wire. The current is in this direction and we curl towards the magnetic field, so that's coming out of the board. We'll have a force, say, upwards on this wire, which is not going to cause a torque, so we don't care about that. Now that could kind of try and alter the shape of the wire to turn it into like more of an oval shape, but we're going to assume that it's tightly wound. The coil is not going to be affected. This is going to have no effect on what we're doing. Okay. Now let's look at this one going into the board here. So again, put your fingers into the board and curl in the direction of the magnetic field. Thumb points down. So we have a force downwards here. And going across this wire, we're going to have the same thing here. We're going the opposite direction. We're going this way. The wire is going, opposite direction since it's underneath. Then we curl, so it's pointing down. So again, there's going to be a downward force on this wire. So like this one has an upward force. I should have left more room between these. So again, the top and bottom wires are kind of being pulled off the coil, but these forces aren't going to be strong enough to change the shape of the coil. So they cancel each other out. We don't have to worry about those at all. We want to focus on these two forces. I am going to move this picture down because it is a little confusing. So yeah, we had a wire like this is supposed to be a square. I drew it more of a rectangle here, but so yeah, that's what the coil looks like. So again, we have an upward force on this wire, which will do nothing. Here, just keep these separate. We have a downward force on these wires, which again do nothing. And then, like this one's going to have a force that's into the board here, and a force out of the board on this wire. And so that's going to cause these will provide the torque that's going to cause this entire coil to rotate. So that's the idea. And what we want to do is calculate the torque on this coil. So first off, what I'm going to do is I'm going to draw a normal line going through the coil. So it's perpendicular to the coil. And we have an angle between, actually I'm going to find a normal vector. And I'm going to pick it going in this direction for reasons we will see later. And so there's going to be an angle between these, like this normal vector and the magnetic field. But when we want to calculate the torque, we're going to have to take this angle into account. We want to find the, we've got the force, the angle it makes with that normal, or this R vector. That's going to matter. I think it's easier to see if we look in terms of lever arms. So the advantage of using vectors here is they define these two directions. So they kind of naturally define this angle. But the lever arm, if we extend this line of force, and we can make a right triangle here. So like the minimum distance from the axis of rotation to the line of force, that's the lever arm. And so an alternative way of looking at torque is just force times the lever arm. So let's do that way. So this is our axis of rotation. Right here, this is the line of force. And so the lever arm would be this distance here. Now it's a little small, it's going to be hard to even write an L in here. Here. I'll just write it over here and draw now. So that's the lever arm right there. Now if this angle is theta, or phi, let's call this phi, then remember this is a normal vector, it's perpendicular to the coil. So let's give it a magnitude for now. Just it's a little bit easier just looking at numbers. Let's say phi is 30 degrees. So if this angle is 30 degrees, this angle is 60 degrees. But remember, this angle is also a right angle. So if this angle is 60 degrees, this angle is going to be 30 degrees. And so we can see, I'm going to expand this triangle. Like here's our force, pointing upwards. Here's the center of the coil. And this is that normal direction. So we drew a normal vector here. And this is the center of the coil. So this distance here is L over 2. Because each segment of this coil has a length L. So we're going from the center to this, this upward wire, which is at the end. So this distance is L over 2. And we have a right triangle here. This is the lever arm here. So I find phi to be this angle between, actually I can change this to theta, sorry about that. So, yeah, let's say this angle is theta. And just numerically, let's say it's 30 degrees. So again, this is a right angle. This is the coil. This is a normal vector. So if this is 30, this is 60, which makes this one 30. And so basically this angle is the same as that angle. Okay, so now from this triangle, we can say sine of theta is equal to, opposite, which is the lever arm, over the hypotenuse, which is L over 2. And so the lever arm, okay, we don't need that anymore. Let's just write down this result. The lever arm is equal to L over 2 sine of theta. And again, it's the angle that the theta is the angle between the magnetic field and that normal direction. Okay, so let me move this, see if I can cram everything in without erasing anything. So I'll just move this over here. So sine of theta is the lever arm over L over 2. Okay, so now we can find the torque is just the force times the lever arm. Well, let's look at the force on this wire. So force is ILB sine of theta. Yeah, I should have probably... I know I want theta to end up in the end, just because that's how it's always written. So yeah, let's just change these angles. We're just calling them different things, so you can do that. Okay, so on this wire, we have to find this angle between the magnetic field and the current. And they're perpendicular to each other. So like here, the current's in this direction, magnetic field is in that direction, 90 degrees between them. So the force is just going to be ILB. So let's call this torque 1. And we'll say this is wire 1. We'll call that wire 2. We don't care about the other ones. So the torque due to this first wire is just a force times the lever arm. So we have ILB times L over 2 sine of theta. Okay. And if we clean that up a little bit, we'd have 1/2 IL squared. Yeah, 1/2 IL squared B sine of theta. Okay, so that's the torque due to this wire. Now, if we look at the torque due to wire 2, notice they're both causing the same type of rotation. So they're not fighting each other, they're working together. So the torque due to wire 2 is going to have the same magnitude and be pushing the wire in the same direction. So the net torque on this wire, let's do this. The net torque on this coil will just be twice the torque due to this wire, so we get rid of that 1/2. So we found the torque on this coil. Now the thing is, this took a little bit of work to do that. And we don't want to have to repeat this process every time we come across a coil. So a couple things we can note. L squared is the area of this coil. So let's replace that. Now we calculated this for a square coil. It turns out if we used a circular coil, we'd get this exact same result, except instead of the area being L squared, it would be pi r squared. So whatever shape your coil is, the torque on the coil is going to be the current in it times that cross-section area times the magnetic field times the sine of the angle. Now, this is a single coil. So what if we took a wire, like what we did is we took it and wrapped it around a square, like a block or something. Again, this was just for calculation purposes. What if we did something more reasonable and we had a cylinder with a circular cross-section and we wrapped it around in a loop? That would be a coil. But we don't have to stop. We can take that same wire and just keep wrapping it around over and over again. And there's going to be a torque on every loop in the coil. So again, this would be the torque on a single loop. If we had a lot of loops, or let's say we have n loops. Then the torque would just be n times, the number of loops times the torque on a single loop. And we're going to define something now. I'm going to write it down. So this is called the magnetic moment. And that's equal to NIA. So N is the number. So a coil has a magnetic moment. And the magnetic moment is equal to the number of loops in the coil times the current times the area of the coil. And once we define this magnetic moment, we can write the torque in a more compact form. We can say a torque is the magnetic moment times the magnetic field times the sine of the angle defined in this picture. Okay, now, so basically what we did, just this whole idea of a magnetic moment, it's like here's the torque, it's got all these things involved. The magnetic moment is a property of the coil itself. And the magnetic field is coming from somewhere else. So we kind of just separated the two things. Like this is our coil, that's a magnetic field, and here is the result, the torque. Now I want to talk about this angle. I defined the magnetic moment here. Magnetic moment is actually a vector, and so it has a direction. So, yeah, like the earlier I drew this as a normal vector. I'm going to relabel this as the magnetic moment vector. Now, one issue though is there's two possible orientations for the magnetic moment. One is in this direction. One is, it's perpendicular to the coil. So there's two directions. So how do we know which one to pick? And the answer is the right-hand rule again. So let's look at this coil. We have the current coming out, and then it goes over and in. So the current is looping around like this. And so if you use your right hand and curl your fingers in the direction that the current is looping around, your thumb points in the direction of the magnetic moment. So if we reverse the direction of the current, the magnetic moment would flip around. If the current was looping this way, then the magnetic moment will be pointing in that direction. Okay, so this is probably a good time to kind of summarize this whole topic of torque on a coil. So, let me clear some room. We've got our results. Torque, we define the magnetic moment, and there's the torque on a coil. And just clean the board, and then this always happens. It looks worse as soon as I erase anything. Guess I should just stop cleaning the board. Okay. So if we want to know the torque on a coil due to a magnetic field, we first have a magnetic moment, which is a vector that we have the magnitude given by this equation. And say we have a coil, I'll just draw it like this, so there's a current looping around. Let's say it's looping around this way. So the current's coming out here, going around this way. And that'll define the direction of the magnetic moment. And if this is placed in an electric field, a magnetic field, the torque is given by this equation, where theta is in the angle between the magnetic moment and the magnetic field. So the magnetic moment has two parts. A magnitude, that's easy, just NIA, there's units of Tesla times meter squared. And again, the direction is given by the right-hand rule. And so, the orientation of the coil will affect how much torque there is on the coil. But now the torque also has a direction. And the coil is free to rotate. The magnetic field is fixed. And what's nice is that the torque is going to cause what the torque is trying to do is line up the magnetic moment with the magnetic field. So it's going to rotate this way. So again, let's look at this. We've got current coming out here, loops around and goes in here. So if you look at this current in the upward portion, it's coming out of the board, and then we curl in the direction of the magnetic field. It has an upward force. This one's going to have a downward force. You can see if it can rotate about this point, it's going to rotate, in that direction. So now that we've completed this, I just wanted to show that's true. So again, like finding the torque and looking at it that way can be fairly complicated. But now, if we know what direction the magnetic moment is pointing, just think that it wants to line up with the magnetic field. So, from this point forward, when you want to know the torque on a coil, use that equation to find the magnitude of the magnetic moment, right-hand rule to get the the direction of the magnetic moment, and then we know the magnitude of the torque and what type of rotation it wants to line the magnetic moment up with the magnetic field. Okay, so I guess there's 4 steps involved, but none of them are too difficult by themselves. The only thing that might be confusing at first, it's not hard once you get used to it, but getting the direction of the magnetic moment right. That's probably the most difficult part at this stage. Once you learn it, just curl your fingers in the direction of the current, thumb points in the direction of magnetic moment. But again, the right-hand rule is one of those things that just takes some getting used to. It's not complicated, but you definitely have to use it a lot before it really starts to make sense. Okay. Now, in a sense, we're done talking about torque on a coil. We figured out what we needed to figure out. But you might be wondering, why do we care about this? Is this something that actually matters? And the answer is yes. This is actually a very important thing. Let's say we have this coil that's actually free to rotate. And so we set it up like this, we establish a current, and what's going to happen? Well, it's free to rotate in any direction. It's going to rotate towards the magnetic field. The magnetic moment, it wants to line up with the magnetic field. And once it does that, then theta is going to be 0. If they're parallel to each other. And the torque, sine of 0, is 0. So like here, the torque is relatively large, but the torque is decreasing, and then it's going to be 0. Remember, torques cause angular accelerations, so here the angular acceleration is 0. But it'll have angular momentum, and so it's going to keep on rotating, and now the torque is trying to spin it the other way. So it's still moving this way because of momentum, but the torque is going the opposite sense, so eventually it's going to stop and swing back. And so if you were to release this, what it would do is something like this. It would oscillate back and forth, and then eventually settle down and stop because of friction. Now, that does not seem like a very big deal. So we can get something to spin around for a little while before it comes to rest because of friction. And that's true. That is not very useful by itself. However, now, maximum torque will occur in this orientation. If this is our magnetic moment, it's perpendicular to the magnetic field, 90-degree angle. So like the maximum torque we could get is a magnetic moment times the magnetic field. Okay. So you got maximum torque, it decreases to 0, and we can turn this into something that is actually very useful. So let's say we set it up like this, and it's going to, as the coil rotates, the magnetic moment rotates with it. What if we get to this orientation? So it's been accelerating, the acceleration goes to 0, but now when it passes, we're slowing down. This magnetic field is going to be slowing it down. But what if when we get in this orientation, we reverse the direction of the current? The effect would be to flip the magnetic moment over. So let's say it goes a little bit past the magnetic field, and it flips over, and now the torque is going to cause it to accelerate, in the same clockwise direction until they line up again. And then what if we flip the current again? Then this is going to flip over. And so if we can achieve that, if we can get it so every time the magnetic moment lines up with the magnetic field, if we can reverse the direction of the current, then we can have this thing just continue to spin in one direction. And so that is something that you might be able to see the uses for. Basically, we've created an electric motor. Where we have to supply energy for the electricity. We have to establish a current. So we are giving energy to this. We're giving this electrical energy and turning it into mechanical, rotational energy. And again, that has tons of uses. Electric motors, they're in a lot of things. Your computer probably has one, like the hard drive. It's or like actually, I don't know if they do. You might not even be familiar with these disks anymore, but yeah, they store data on disks. I don't think computers even have those anymore. But yeah, when you put it in there and it spins it around. They used to have music on those called CDs, record players. I guess they're making a comeback for whatever reason. Yeah, that would use an electric motor. You plug it in, you power it up, and it causes the record to spin around. Nowadays, they can even make motors powerful enough to move a car, like Tesla, or I think Chevy has one, or like a Volt or something. So yeah, you can actually power an entire car with an electric motor. So again, these have uses all over the place. They are very important. Now, it's kind of difficult to explain this whole process of how you get the magnetic moment to flip around. And so what I did is I found on YouTube, there's a really good, someone did a great job with the graphics, explaining an electric motor. And again, the one I described is very simple. Like you just have this loop, and you can imagine if you're running this, what's going to actually happen is, like you have maximum torque here, maximum torque here, and then the torque decreases, and then you flip around, and so, again, you still have low torque until you get here. Torque is going up and down. If you were to just follow it through its entire cycle, the torque is oscillating. And so, the angular acceleration is oscillating as well. And turns out you can actually build a motor just using some simple wire and some magnets. It's really all you need, and just structure, like you can use paper clips or whatever. Yeah, it's not even hard to build your own motor, and we've had labs before where you do that, and you can actually see them like speeding up and slowing down. So this is like what I've described as an incredibly simple motor. It can definitely be improved on. And so, yeah, I found a video that was just, the graphics are really good. And kind of explaining, I definitely recommend watching this video. They use computer graphics and can just try to draw it on a board, but when you see it, it doesn't leave any questions. Yeah, it's a really well done video, so I recommend watching that. Yeah, I think that is it for now. Oh yeah, there's a picture in the notes of an electric motor, but yeah, watch the video. You can actually see it in action. It's much better than just looking at pictures. Okay, so that'll be it for this video. And then we're going to go on to something entirely new next time.